So, good afternoon, everyone. Welcome to the course Design of Steel Structures. I am Danish Bashir from IIT Madras. I will be your TA for this course throughout this semester. So, I hope all of you have joined the online, have enrolled yourself in the online portal of NPTEL, and you have gone through the course content there as well as the syllabus there. And I hope you are regularly following the video lectures that are being uploaded there. This course is being offered by IIT Kharagpur this semester. So, what will be the procedure followed for the weekly live sessions that I will be going to conduct? I will be going to conduct 12 live weekly sessions, and I think there will be one more additional session which we will see at the end of this course. So the procedure that will be followed is like whatever will be taught within a week, that those concepts will be discussed briefly on Saturday between 3 to 5 p.m. All those concepts, we will try to solve numerical problems regarding those concepts as well in the weekly live sessions. And whatever you people will be having doubts, you are welcome to ask those doubts after 1 hour of the live session, because the live session is for 2 hours. For first 1 hour we will discuss the problems and the concepts. In the second hour I have kept that hour for you people to ask the doubts. I will be very happy to share whatever I know about this course and to clear your doubts. So regarding the design of steel structures, is the basic, or what I can say, it is an introductory course into the design of structures which are made up of structural steel. Like you people have also well aware of the course like design of reinforced concrete structures. That was also an introductory course. Some of you might have attended my weekly live sessions on that course as well, where I was the TA of that course as well, design of reinforced concrete structures. Similar to that course, this course will be offering you the design practices that are being followed in the design of steel structures. It's a bit different from that course in the way like it has a totally different code apart from IS 456. Like in this we follow IS 800 and other design codes as well. So I hope all of you people are aware with the codes that we will be using for this. And I assume that all of you will be having IS 800 codes with you, because that will be the prerequisite of this course. And one more important thing is that since this is an introductory course, and I hope you all people will be having a knowledge of basic structural analysis, because that is also essential, like shear force diagrams, bending moment diagrams, axial force diagrams, that are very essential because this is a design course. So I hope all of you people are aware with the analysis part, because that should not come in the way, or that should not be a bottleneck for solving design problems. After that, first thing is that design code, and second thing was this structural analysis. In today's live session, that is the week one of the live sessions, I will be giving you the basic introduction or the general considerations that are being considered in design of steel structures. Followed it, we will be seeing some loads that are that apply on our steel structures, and there and we will see the specific calculations of the design of wind loads. That's important because there are other calculations like calculation of the wind loads we will be seeing, but there are other calculations like calculation of seismic forces. I think that is not important in this weekly live session, and I think those concepts you will get very well in earthquake resistant design ERD subject, and that is beyond the scope of this course, and you see those things in your ERD classes. And but wind calculation of wind load is being included in design of steel structures. I will be following the book written by SK Dougal. There are other authors as well, but primarily I think your course instructor from IIT Kharagpur is also following the same book. I have not checked that with. You can check it on the online website of NPTEL, Design of Steel Structures. Just search this. You will get the YouTube videos there, as well as course content and the assignments. So most of the you students will be having questions like, we are expected to solve assignments here, but I have seen the assignments. Those assignments are very basic assignments, though those assignments you can solve yourself at your place, and if you have any doubts, you can come up with those doubts to me. Here I will be solving some standard or some little bit advanced problems on design. So it will help both you to get very good grades in the examination. Like those are a bit standard problems than your assignments. Assignments contains just the question MCQs, and I don't think that will suffice you for passing this course. So stay tuned with me for this weekly live session. So for today, it will be the introduction. So starting with the introduction of the for the design of steel structures. Let me write what is the week first. Week first, and the date is 27/07/2024. Okay. So introduction. What actually is the design of steel structures? So in simple words, we can say that the design of steel structures involves the planning of the structure for specific purposes, proportioning of the members to carry the loads in the most economical manner, and consideration for erection at the site. So there are three basic things that we saw in this definition: is the planning of the structure, that is the first thing, planning of the structure. Second is the proportioning of the members, that is comes in the design process as well. How we have to proportion our member, like we need to design a beam, or we need to design a column. What will be the optimum section for that? That comes in the design problems. And that should be also in the most economical manner, because we cannot just waste the material here and there, and then I say that I have designed this section. That will be the uneconomical. Like if we have any member, we have designed any steel member, and we are using something, for example, we are using a area of cross section for to carry the loads. But when we carry the analysis, we see that only 50% of a is being utilized for carrying the roads. So if we see that the 50% of the area of cross section is not being used, so it is a huge wastage of the material. That is 50% of the material there in itself is not being used for carrying loads. So it's important for proportioning the members in an economical way for carrying the loads. And the third, final, and last point is consideration for the erection at the site. So how we have to erect the members at the site, that we have to see. That is the first important objective of the design of steel structures. Sorry for the little disturbance. So I was discussing that the 50% of the material is not being used to carry the loads. So it's the wastage of the material. So then we have to see that the design that we have done, it should possess the adequate strength to withstand the direct and the induced forces to which it may be subjected during its lifespan. So one more important thing is its adequate strength. It should have adequate strength. Adequate strength to withstand direct and induced forces. Induced forces during its lifespan. So if there is inadequate strength or there is an inadequate assessment of the strength, that will be very disastrous to our structure. Like if there comes the snow load or the seismic load that act, or the wind load that will act on our strength structure that is beyond its strength, then it will be very hazardous for that structure. So in design process, we have to consider those things as well. Um, uh, so in nutshell, I will tell you the design of the structures or the steel structures usually includes, first it includes functional planning, and then it includes the strength of the materials and the design methods. So what is first the functional planning? So in functional planning, it takes consideration in the overall takes into the consideration the overall planning of the structure in accordance to the purpose it is meant for. It also includes the layout and the proper arrangement of the space. Functional planning involves a lot of imagination and is done with the help of architects. Okay, this is the basic definition of the functional planning. It is just the planning of the structure that we are going to build using our steel material. So then it involves second point is design of the structural elements. So for designing the structural elements like beams, columns, trusses, purlins, etc., on the plan provided by the architect, we have to consider the different design considerations. So for that, a designer should take care of a lot of things like uh, the things that a designer has to take care is the architect should not have given a type of section that is not available in the local market, like unusual sizes or the rare roller sections should be avoided. In steel structure buildings, the various elements should be compatible at the joints. Like if you are making one beam with one type of section and another beam with other type of section, those should be compatible at the joints. So this has to be taken care by the structural engineers. The steel structure is exposed to in exposed conditions require frequent maintenance that has to be taken care of as well. And one of the important thing about our sections is that transportation facilities for built-up sections should be explored before designing them or before precasting them. Like then the another step in design process involves the erection. Steel structure elements should be erected with proper care, avoid secondary stresses. Like for example, when some huge I section or C section is being erected for a column, so it should be properly handled and erected in a manner so that it does not induce any secondary stresses into it, because it will create a lot of problems when the structure will be in its during its service life. It will create issues for that structure. The section should be of the size which can be easily erected. Also, that is also important. And then in the design process there comes the standard specification and the codes for the safe and economical design of the sections. Actually there are standard specifications. There are standard specifications and the codes available on the past design practices. These are being prepared on the past design practices actually. and as well as experience also, and the behavior of the existing structures, knowledge gained from the failures, and from the fresh research data as well. So you got the idea from where these design codes come from, or the from where these standard specifications come from. These actually are from the experience of the past design practice, or based on the behavior of the existing structures, or the knowledge gained from the failures, the structures that have fallen down, or from the existing research data or the research that is going on. From time, these design codes get revisions, and new provisions are being added from time on time, depending on the type of the research that is being carried out. So this is being held taken care by Bureau of Indian Standards, and it publishes a number of codes for the steel structures as well. So for getting the properties of the structural steel roller sections, like what I meant by the properties, for example, I have some I section. You want to get that is a standard I section available in the market. Now you want to get a handy detail about its properties, like area of the cross section. You want to get the properties like moment of inertia about x-axis, like y-axis, like z-axis, its polar moment of inertia. All the other details, those are available in IS handbook on number 1. Okay. For design loads for buildings and structures, we follow IS 875, and this code is of 1987 version. IS 875 gives us the design loads on buildings and structures that we have to follow in this course as well. And one of the important codes is IS 800 of version 1984, and it is for the code practice for the use of structural steel in general building construction. I hope you got all the three basic codes that we are using. One is IS Handbook number 1, another is IS 875, and another one is IS 800. IS 875 is for design loads on buildings and structures. IS 800 is for the design of steel structures, structural steel for general buildings. I hope up to this point this is clear to you. Now, since we are moving from reinforced concrete structures to steel structures, so there should be some advantage why we are considering these steel members or steel structures. That's why we are opting for these. So, looking at the structural steel has many advantages to be used as a structural material. So, for example, if we take a structural member, it has a very high strength per unit weight. So it means that it's for a given weight of a structure, given weight of a steel member, it is having high strength compared to the other counterparts. Like if we see a RC member, it has a high strength to it is unit weight. Because of this property, steel member of small sections which has little self weight is able to resist heavy loads. So very small sections, cross sectional area sections with very small cross sectional areas are able to withstand very high loads. So you might have observed this in practice also. If we see at two different bridges, one bridge is made up of reinforced concrete or pre-stressed concrete girders, and another bridge is made up of steel girders. You can easily tell that the cross-sectional area of the steel girders is very small as compared to the pre-stressed concrete girders. This is only because of high strength per unit weight of the steel material. That's why the cross-sectional area of the steel members is very less as compared to RC members. So because of this lightweight property, steel members can be conveniently handled and transported as compared to RC members. For this reason, prefabricated members can be frequently provided. Okay. So if another property of these of steel to be used as a structural material is that if these steel structures made of steel are properly maintained, they can have a very long life. Okay. One more thing is that the property of the steel mostly don't change with time. This makes the steel most suitable material for the structure. Okay. This is one more important property. As you are well aware of the fact that steel is a ductile member as compared to reinforced concrete that is brittle, or the concrete that is brittle in nature. So it does not fail suddenly. So if a structure that is made up of steel has to fail, it gives visible evidence of impeding failure by large deflections. So for example, there is a beam made up of steel member. So if its load carrying capacity or the load on it has exceeded its load carrying capacity, it will not fail suddenly. It will give an visible warning, or it will give an visible evidence of its failure by having very large deflections. As compared to RC members, there is a certain failure of the concrete, but in our steel members, there will be visible large deflections that will give us the evidence of an impeding failure. So, since these steel members are joined by joints or by welds, additions and alterations can be easily made as compared to RC members. Like in RC member, if you put the concrete and the reinforced steel at one time, then you cannot add more to that beam, or you cannot add a column to that beam, existing beam, like that, if it has been completed. So addition and alterations are not possible in RC structures, but in steel structures it is possible. And because of very light weight, they can be erected faster. That is one more advantage of steel structures. Hmm. So if we see that steel has the highest scrap value amongst all building materials. Like if we demolish a building made up of reinforced concrete, then what we will get? We will get only dust, recycled aggregates, and damaged steel. It doesn't have that much scrap value. But if we demolish a steel building made up of steel members only, we can easily take those steel members and can use into another building, because steel members have, it means that steel members have high scrap value amongst all the building materials. So there are some disadvantages as well for the steel to be used as a structural material. Like when the steel is placed in exposed conditions, um, corrosion happens. So it requires frequent painting. So all the steel members in our steel structure should be frequently painted because it is on the verge of corrosion if it is exposed to external environment. One more important disadvantage is steel structures need fireproof treatment, which increases the cost. They are very prone to the fire hazard, so they need fireproof treatment, which increases the cost of the steel structures. So this was the advantage and disadvantage of steel structures. Then we have structural steel that is available to us in the market. Like there are the different properties that we can discuss also. Let me. So properties, mechanical properties. Of structural steels. What are the different mechanical properties? So if we look at the first property of the structural steel, that is the yield stress. Yield stress. Fy we denote yield stress. The structural steel that is available in our market, it is yield stress ranges from 220 to 540 pascals or Newton per mm square. Okay, and The second most important property of a structural steel is the ultimate tensile strength. Ultimate tensile strength. Fu, and it is about 1 to 1.2 times Fy. Okay, and third property is the percentage elongation or the percentage strain. Percentage location. I am writing down this value for low carbon steel because there are two types: low carbon steel and high carbon steel. I am writing the value for low carbon steel. For low carbon steel, it is percentage elongation is 20%. Okay. Uh, then another important property is the modulus of elasticity. Modulus of elasticity. Okay. So modulus of elasticity E is, it's a well-known modulus of elasticity, 2 into 10 to the power 5 Newton per mm square. Okay, or 200 GPa. Fifth property is shear modulus. It is 0.4 times E. Okay, Poisson's ratio. Poisson's ratio. Mu. And there are two values of the Poisson's ratio. First is in elastic range, because steel behaves differently in elastic and plastic ranges. I will show you the stress strain curve of steel as well. So for elastic range, the Poisson's ratio value is 0.3, and for plastic range, it is about 0.5. Okay, I hope this is clear to you. Now let us study about the stress strain curve of this steel. I will give you the brief concepts regarding the stress strain curve. So the nominal stress strain curve for mild steel looks like this. Okay, you people have always all seen this curve in your basic courses. So everywhere we study this stress strain curve for mild steel. So let us see the different points. So if I look at the range on OAB, what is the range OAB from this to this range OAB? So what it is known as, it is represents a strain line that is within this the stress produced. The stress produced sigma is directly proportional to the strain produced, and within this range the steel obeys the Hooke's law, OAB range. Okay, so it obeys Hooke's law. Okay, when we go a little bit further from this, and there are some names to these points as well. So like point A is well known by the name is the limit of proportionality. Okay, limit of proportionality. So like stress is directly proportional to strain up to point A. Point B marks the end of the elastic limit. Okay, so it's the elastic limit. What is the elastic limit? Like if you stress or if you give the load to the material up to elastic limit, like there won't be any permanent deformation. The structure will come to its original state on the removal of the stress or the removal of the loads. Represents the elastic limit. Then C dash C. Okay, C dash C represents the what this C dash actually, this is not visible actually, like you can see from this C dash. C dash has a name and it's known as upper yield point. Okay, actually at this point steel starts yielding. Okay, upper yield point. And this C, this is lower yield point. Okay, it's lower yield point. Then after that, so what happens in this region C dash C is that the stress is at which there is a definite increase in strain without any further increase in stress. So in this yielding, what happens in the yielding region is that it starts to yield strains or the elongations increase in our steel specimen without any increase in the stress. Okay, so this is the yielding zone. After that, we have a region called CD region. We have a region, sorry, we have a region, we have this region, CD region. Okay, I hope that is visible to you. It represents plastic yielding. Okay, so now the plasticity has started. Plastic yielding. So what I meant by this is that, so for example, if at point D you will remove the loads or you will remove the stresses from your steel specimen, it will not retrace the part like D, C, C dash, B, A to O. It will be having some permanent deformations. Okay, that's why we call it as plastic yielding. Okay, CD. Then plastic yielding. Okay, then DE. What is the region from D to E? This region. Okay, D region. What we call this D region as? This is strain hardening region. Okay, we call it as strain hardening. Hmm. So it's called strain hardening because it's the range where additional stresses produces additional strains, and in this region, strain increases faster till the ultimate load is reached, and E point is known as ultimate stress. Okay, ultimate stress. So it is the maximum stress that our specimen can bear. After that, uh, EF region is known as, I will show by a different color. EF region, this region. Okay, EF region, it is known as, here actually stress falls, here the opposite is happening, stress is falling and with rapid increase in strain, rapid increase in strain. Okay, so ultimately at the point F, the specimen breaks. Okay, and this is known as breaking stress. Okay, breaking point, breaking stress. So these are all the different points or the different regions in our stress strain curve of mild steel. I hope you people got the basic idea regarding the stress strain curve. Okay. Then we have rolled steel sections in our this rolled steel sections. So in design process outlined earlier, one of the objectives and the primary emphasis is the selection of the appropriate cross sections for the individual members of the structure being designed. So mostly these these roller steel sections are available in market. We take these steel sections and then design our member as per the specific requirements. Okay, so different sections that are available are like we have rolled steel eye section. This rolled steel eye section is there. We have rolled steel channel section. This is channel section is there. We have rolled steel T section is there. We have rolled angle sections are there. Okay, we have rolled tube sections. These are angle sections. All these are angle sections. Okay, okay. These are tube sections, and we have steel bars as well. Okay, these shows the steel bars, and we have flat plates as well. Okay, plate sheets etc, those come in these regions. So in I sections you already know from design of reinforced concrete structures that this portion is called the flange of the I section, and the middle portion is called the web of the I section. Okay, this is clear to you guys. And in C section also it will be upper and lower parts are known as flange, and middle part is known as web. Okay, flange and web. And in ankle section these are known as flange, these are known as legs. Keep that in mind. Okay, like this is a tube section, this is angle, let me write, this is I, this is I section, this is channel, this is channel section, this is T section. Okay, then these are uh, angle sections. This importantly is a tube section. Okay, these are steel bars, plates. Okay, plates, strips, and whatever there is, plates, sheets, yeah, strips. Okay, okay, these are the rolled steel sections. So and there are other types of sections as well, like built-up sections. Those are having some additional components attached to them. Like we have I section with cover plates. Like it looks like this. This is an I section into this. This is an I section, and these are cover plates. Okay. So these are required in different situations, like when we want to increase the bending capacity of our steel member. So we use different types of methods, like we put the cover plates to increase its bending capacity. And another type of build-up section is using the rolled plate section. We make a girder like this. Usually you might have seen this type of large girders, plate girders in a bridge. So using welding, like if welding is done here, and welding is done here, like here it's welding, and so this type of like welding here and welding here, this type of section is known as welded plate girder section. Okay, then we might be having double angle section, like one angle section is this, one angle section is this. So using these two angle sections, we join them with a plate or some strip at the above, so we call it as double angle section. This is double angle section. Or the same in the case we will be having two channels, one channel is like this, another channel is like this. Okay, so these two channels we attach one strip or one plate at the top, one plate at the bottom. We will form a double channel section as shown by this. Okay, double channel section. So these are the these actually these build-up sections. It depends upon our requirement how we require these on in our structure design. Then one of the important aspects in the design of the steel structures is the load. So for the safe design of the structure, it is essential to have the knowledge of the various types of the loads and their worst combinations that a structure may be subjected to, so that it can easily endure or so that it can easily bear all those loads, whatever will be the worst combination of all those loads throughout the service life or throughout the lifespan of that structure. So we have actually different types of the loads. Nine different types of the loads can be: dead loads, live loads, we have wind loads, we have seismic loads, we have snow loads, okay, we have earth pressures, we have water current load. This is water current load is primarily in the bridge. Okay, we have impact loads like blasts and other impacts. We have temperature and erection effects. Okay, these are the different loads that come into place. One of the important things that we will be seeing into is the wind load. Okay, wind load we will be discussing in detail because all the other loads, dead loads, live loads, we study in reinforced concrete design. We study the worst combination there as well, because you might have studied there 1.5 dead load plus live load. You might have studied this there. These are the worst combinations given by our code. And seismic load we study in earthquake resistant design, and snow load or earth pressures we study in like this is a course in geotechnical engineering. There we study the earth pressures. Okay, these water current, impact, and temperature loads are the beyond the scope of this course. And seismic loads you study in earthquake resistant design. There remains one important load is the wind load. So we will be looking into the wind load. What actually is this wind load? Okay, so we all know that all exposed structures, irrespective of their heights, are affected by the wind forces. Okay, this is very common. Wind is everywhere. So this wind blows against the structure and strikes on its outer surface of the outer shell. So its outer shell experience the effects of the wind force. The wind pressure intensity at any height of the structure depend upon the velocity. It's obvious that what will be the velocity of the wind, density of the air, shape and height of the structure, topography of the surrounding ground surface, and the angle of the wind attack. So there are almost there are six factors on which the wind pressure intensity at any height depends. First is the velocity, second is the density of the air, third is the shape of the structure, fourth is the height of the structure, fifth is the topography of the surrounding ground surface, and sixth is the angle at which the wind attacks on our structure. Okay, so looking at all these things, we want to now calculate the design wind speed at any height. What will be the design wind speed at any height on our structure? So I already told that the for loads IS 875 1987 version we use. So it relates the basic maximum wind speed. It has uh, fixed the basic maximum wind speed throughout the India, and it is denoted by VB. It is for a very short interval of time for 3 seconds, and there is also a return period, in how many years this type of wind can be expected on a structure. That we term that period as return period. Like for 50-year return period, we define the basic maximum wind speed. Mm. And it is different for different zones in our country. Okay, so that basic wind speed VB is there. So from that VB, we know we term it as basic maximum wind speed. Okay, speed. So this is related to the wind speed, design wind speed at any height, VZ. Okay, VZ, VZ design wind speed at any height Z in meters per second is equal to the basic maximum wind speed VB. Okay, times the three coefficients. K1, K2, and K3 that take care of all the six factors that I already mentioned. Okay, so out of K1, K2, K3, K1 is the probability factor or the risk coefficient. K2 is the terrain, height, structural size factor. Okay, and K3 is the topography factor. Look, all six different things have been taken care by these three factors. Okay, and these values of these three k factors we can easily get from our code IS 875 1987 version. Okay, so after we got the uh, design wind speed. Okay, design wind speed. After getting the design wind speed, we need to calculate the design wind pressure. Okay, design wind pressure. So this design wind pressure is given by PZ is given by zero point 0.6 of VZ square. That is zero point 0.6 times square of the design wind speed. Okay. So actually, you will see zero point 0.6 is having some units here, and V square is also having some units here. So always remember that if the velocity is in meter per second, the design wind pressure is Newton per meter square. Okay, so it is an empirical formula like this. After this, from the pressure, we can easily calculate the wind force. So the total wind force or the wind load acting on a building is given by CF times A times PZ, where CF is again one more coefficient. That's the force coefficient for the structure, and it is given in the code IS 875. If you want to look for the different coefficient for different buildings, A is the effective frontal area, that is the effective area on which the wind is striking, effective area of our structure, and PZ is the design wind pressure that we already calculated, and that is given by zero point 0.6 of VZ square. Okay, so if we know the different factors for our structure K1, K2, K3, we can easily, and the basic maximum wind speed VB, we can easily calculate the design wind speed VZ. After calculating the design wind speed VZ, we can easily calculate the design wind pressure VPZ, that is zero point 0.6 of VZ square. After calculating the PZ, we can easily calculate the design wind force on our structure or the design wind load. That design wind load we can take the into the consideration in our design process, and we can accordingly design our members. So regarding the same thing, we will follow some numerical problems. So example first is, so the first example is estimate the design wind pressure on a 100-meter high lattice tower located on outskirts of Allahabad. Estimate also the wind load in terms of effective frontal area of the tower. So for Allahabad city, like in the code IS 875, you have to look for all the three factors K1, K2, K3. After getting all the three factors, and for Allahabad region, you will have to select the zone as well, and you will have to get the basic maximum wind speed VB. So looking at the code that is given as 47 meter per second. Okay, you got the basic maximum wind speed, and K1 for the Allahabad is in code, it is equal to 1.07 with an return period of 100 years. Okay, and after that K2 K2 is equal to 1.17, and this is a category 2 building of class C. I cannot explain everything here. For this, you have to look into the code IS 875 and find all these things there. Okay, K3, since we are calculating for the ground level. Okay, so 1.0 for ground level. Okay, so our design wind speed. Okay, design wind speed Vz is given as V basic times K1, K2 and K3. Plugging in all the values, we get the design wind speed as 58.84 meter per second. Okay. So the design wind pressure will be design wind pressure PZ is 0.6 times VZ square. So plugging the value of VZ, we get the PZ value as 2077.29 Newton. This is in Newton per meter square. Okay, per meter square. Okay, so design wind load. So design wind load will be given as F CF times frontal area AE times design wind pressure PZ. Okay, F. So force coefficient, let us take force coefficient 2.7. A is the frontal area, PZ is the 2077.29. It comes out to be 5608.68 frontal area AE newtons. Okay, so this is the design wind force that we get. So example 2 is the calculate the design wind pressure for a 12-meter high water tank locating in MNIT staff colony Allahabad. So similarly, for Allahabad you calculate K1, K2, K3. Okay. After K1, K2, K3, get the and VB, get the design wind speed VZ to be equal to K1, K2, K3, VB. This is a homework for you. After getting this, okay, calculate the design wind pressure PZ, that is 0.6 of Vz square in Newton per meter square. Okay, calculate this from PZ. Calculate the wind force wind force F given as force coefficient CF frontal area AE times PZ. Okay, that is the homework for you. So in today's live session, we saw the introduction and the general consideration in the design of steel structures. After that, we saw the advantages and disadvantages of steel as a structural member. We saw the structural properties of mechanical properties of the steel structure. Then we studied the mechanical stress strain curve of the mild steel. After that, I gave you the introduction about the different loads acting on our steel structure, and we importantly saw the calculation of the wind load on our structure, in which we saw the design wind speed, design wind pressure and design wind load on our structure, and solved the numerical problem as well. If you people have any doubts, you are welcome to ask. If you don't have any doubts, please disperse. Thank you everyone for joining this session.